I, of course, have been going to the Arctic for quite some time, and I was flying over a lot of area that we've done a lot of work on and study over the years. And here there was no ice. We look down and see waves that look like the middle of the Pacific Ocean or something. So it was pretty unusual.
More than unusual, in fact, a new record low. The National Snow and Ice Data Center reports that by the fall of 2012, the sea ice extent fell to the lowest level since 1979, when satellite mapping began.
My name is Mike Steele, and I'm a physical oceanographer at the Polar Science Center at APL. My role in what we call SIZRS, the Seasonal Ice Zone Reconnaissance Survey, is to deploy what I have named up-tempo buoys, that stands for upper temperature of the ocean, which will be pushed out the back of these Alaskan Coast Guard C-130 planes, land in the water. The buoy will deploy a 60-meter long string of ocean thermometers, we call them thermistors, that will measure the changes in the upper ocean during the summertime and the fall, and hopefully through the winter and into the next summer as well.
Our part of the SIZRS project is to drop expendable probes that have a sensor package that falls through the water and measures temperature and salinity.
This ice cover lid that used to cover the Arctic even through the summertime, when it melts away, the sun can warm up the ocean. Also, warm currents coming from the south can enter the Arctic and warm the ocean as well. Those are the two main sources of heat for the Arctic Ocean. And my buoys, my up-tempo buoys, are designed to try to measure that warming.
I've often felt that the ocean exerts a strong control on the minimum ice extent. And prior to the last 10 years or so, you pretty much could find the ice, most places, tended to remain over deeper water. The ocean is losing control. The ice is receding way back from the boundary between shallow water, the shelves, and the deeper ocean. So I'm really interested in why that's occurring, and how the atmosphere is suddenly taken over from the ocean, or has the ocean changed itself? So it's a hot question.
The model that we use here at the Polar Science Center to simulate what is happening with the ice and ocean in the Arctic. This model we call POMAS is what we call a coupled ice-ocean model. The model represents the ocean temperature, currents, salinity, the ice thickness, the snow depth, and the motion of the ice. The ice has been thinning in the Arctic dramatically over the years. One way of representing that thinning is to compute the total ice volume in the Arctic. And the downward trend in ice volume is significantly smoother than the ice extent trend. Because the ice is gone, the ocean is absorbing a lot more heat than usual and is warming up. So what happens to that heat? It is conceivable that all that heat is lost very quickly in the fall because it is cold up there. Or it could be that that heat is sequestered within the ocean and slows the ice growth throughout the entire winter, thereby creating a thinner ice pack at the end of the winter. So the relative strength of those two processes is still a research question.
So one of the things that changes, for one, is you open up the ocean and you likely get more evaporation. That could lead to more clouds. The other thing that's happening is that you're changing the structure of the atmosphere. Typically, the sea ice is colder than the atmosphere, at least sort of in the transitional seasons, spring and fall. But when you open up the ocean becomes relatively warm in the summer. All of a sudden, the structure of the atmosphere changes, and that may feed back again on clouds. It may cause changes in wind speeds. We've noticed in some modeling experiments, for example, we've seen, like, if we take the ice out of the models, all of a sudden the surface wind speeds increase. And that again can feed back on some of the ocean processes that can shift the ice around differently. I think those are active research questions, and it will take some time to sort that out.
Science at work for you. This is APL, the Applied Physics Laboratory at the University of Washington in Seattle.